This is Chapter 12, Module 3, the Resting Membrane Potential. The learning objective of this module is 1. Explain how the resting membrane potential is created and maintained. The transmembrane potential is the electrical difference between the ion concentrations inside of the cell and outside of the cell. It is called a potential because it has the ability or potential to change. The transmembrane potential can either be a resting potential, a graded potential, or an action potential. A resting potential is the transmembrane potential of a resting cell. A change in the resting potential of a neuron would initiate neural activity. A graded potential is when a stimulus produces a temporary but localized change in the resting potential. The effect of this change will decrease with distance from the stimulus. An action potential is a change in the resting potential that is large enough to propagate or spread along the surface of the axon, and it does not diminish as it moves away from the stimulus. The action potential travels down the length of the axon of the presynaptic cell to the synaptic terminal or synapse, where a neurotransmitter will be released via exocytosis into the synaptic cleft. These neurotransmitters will bind to receptors on the postsynaptic cell membrane, changing its permeability to sodium. This mechanism is very similar to the events at the neuromuscular junction. The postsynaptic cell will respond, but the response will depend on other factors, such as what other stimuli are influencing the cell at the same time. The integration of all these different stimuli is called information processing in the nervous system. There are three important concepts regarding the transmembrane potential. First, the extracellular fluid and the intracellular fluid differ in ionic composition. The extracellular fluid contains high concentrations of sodium ions and chloride ions, whereas the cytosol contains high concentrations of potassium ions and negatively charged proteins. The plasma membrane is not freely permeable to ions. If it was freely permeable, diffusion of ions would continue to occur until equilibrium was reached and an equal distribution of ions across the cell membrane was reached. However, the plasma membrane is not freely permeable, so equilibrium will not be reached. Ions can't cross the lipid portions of the plasma membrane. The ions can enter or leave the cell through membrane channels. There are many types of membrane channels, including leak channels. Ions move through leak channels when the cell is at rest or undisturbed or at resting potential. These leak channels are always open, and the movement of ions through these leak channels is a passive process because the ions diffuse down their concentration gradients, that is, from higher ion concentration to lower ion concentration. The permeability of the membrane varies by ion. It is easier for potassium to diffuse out of the cell through leak channels than it is for sodium to enter into the cell through leak channels. So there will be more potassium in the extracellular fluid near the cell membrane than there is sodium in the intracellular fluid near the cell membrane. There are also negatively charged proteins in the interior of the cell. As a result, the membrane's inner surface has an excess of negative charges with respect to the outer surface. The passive processes are both chemical and electrical in nature. The chemical processes are due to the concentration differences of the ions. The intracellular concentration of potassium ions is high compared to the extracellular concentration of potassium ions, so these ions tend to move out of the cell through open potassium channels. The movement is driven by a concentration gradient or a chemical gradient. Similarly, a chemical gradient for sodium ions tends to drive those ions into the cell. Potassium ions leave the cytoplasm more rapidly than sodium ions enter because the plasma membrane is much more permeable to potassium than to sodium. As a result, the cytosol along the interior of the membrane exhibits a net loss of positive charges, leaving an excess of negatively charged proteins. At the same time, the extracellular fluid near the outer surface of the plasma membrane has a net gain of positive charges. The positive and negative charges are separated by the plasma membrane. Positive and negative charges attract one another, and this causes an electrical gradient as the charges are attracted to one another. The intracellular concentration of potassium ions is high, whereas the extracellular concentration is very low. Therefore, the chemical gradient for potassium ions tends to drive them out of the cell. However, the electrical gradient opposes this movement because potassium ions inside and outside the cell are attracted to the inside of the plasma membrane and repelled by the positive charges on the outside of the plasma membrane. The chemical gradient is strong enough to overpower the electrical gradient, but the electrical gradient weakens the force driving potassium out of the cell. The extracellular concentration of sodium is high, whereas the intracellular concentration is very low. As a result, there is a strong chemical gradient driving sodium into the cell. In addition, the extracellular sodium ions are attracted by the excess negative charges on the inside surface of the plasma membrane. Both electrical forces and chemical forces drive sodium into the cell. With a resting cell at the normal resting potential, the cell must pump out sodium ions that leak in and recapture potassium ions that leak out. This pumping is done by an active exchange pump that is powered by ATP. The ion pump is called the sodium-potassium exchange pump or sodium-potassium ATPase. This pump exchanges 3 intracellular sodium ions for 2 extracellular potassium ions. In a resting cell, the pump ejects sodium ions as quickly as they enter the cell. In this way, the exchange pump exactly balances the passive forces of diffusion and helps to keep the resting potential stable because the ionic concentration gradients are maintained. This ends Chapter 12, Module 3, the resting membrane potential.